ಆನ್ ಮಾಡಿ ಓಡಿ 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 ಸಿಂಗಲ್ ಆನ್ ಮಾಡಿ ಅಲ್ಲಿ ಓಡಿ 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 ಆನ್ ಮಾಡಿ
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. ರಾಷ್ಟ್ರೀಯ ವಿಜ್ಞಾನ ದಿನಾಚರಣೆ ಅಂಗವಾಗಿ ಹಮ್ಮಿಕೊಳ್ಳಲಾಗಿರುವ ಇಂದಿನ ಈ ಅರ್ಥಪೂರ್ಣ ಸಮಾರಂಭಕ್ಕೆ ಆಗಮಿಸಿರುವ ಎಲ್ಲ ಮಹನೀಯರಿಗೆ ಹಾಗೂ ಮಹಿಳೆಯರಿಗೆ ಮೈಸೂರು ವಿಶ್ವವಿದ್ಯಾಲಯದ ಪರವಾಗಿ ಆತ್ಮೀಯವಾದ ಸ್ವಾಗತವನ್ನ ಬಯಸ್ತೇನೆ. ಕಾರ್ಯಕ್ರಮದ ಮೊದಲಿಗೆ ಪ್ರಾರ್ಥನೆ. ಗೀತೆ ದಯಮಾಡಿ ತಾಯಿ ವಾಗ್ದೇವಿ, ರಚನೆ ಮತ್ತು ರಾಗ ಸಂಯೋಜನೆ ಶ್ರೀ ಜಗನ್ನಾಥ ವಿಠಲರು, ರಾಗ ಧರ್ಮಾವತಿ, ತಾಳ ಏಕತಾಳ. ಹಾಡಲಿರುವವರು ಲಲಿತ ಕಲಾ ಕಾಲೇಜಿನ ವಿದ್ಯಾರ್ಥಿನಿಯರು. ರಸಋಷಿ ಕುವೆಂಪು ಅವರು ತಮ್ಮ ವಿಚಾರ ಕ್ರಾಂತಿಗೆ ಆಹ್ವಾನ ಎಂಬ ಕೃತಿಯಲ್ಲಿ ಹೀಗೆ ಬರೀತಾರೆ: ವಿಜ್ಞಾನ ಸಂಪನ್ನವಾದ ಪಾಶ್ಚಾತ್ಯ ನಾಗರಿಕತೆಯು ನಮ್ಮನ್ನ 200 ವರ್ಷ ಆಳಿದ್ರು ಅವರ ಯಂತ್ರ ನಾಗರಿಕತೆಯನ್ನ ನಾವು ಅಳವಡಿಸಿಕೊಂಡ್ರೆ ಹೊರತು ಅವರ ವೈಜ್ಞಾನಿಕ ದೃಷ್ಟಿಯನ್ನ ನಾವು ಬೆಳೆಸ್ಕೊಳ್ಳಿಲ್ಲ. ಮತ್ತು ಈ ವೈಜ್ಞಾನಿಕ ದೃಷ್ಟಿಗೆ ತಾಯಿ ಬೇರಾದ ವೈಚಾರಿಕತೆಯನ್ನು ಸಹ ನಾವು ಕೈಗೂಡಿಸಿಕೊಳ್ಳಿಲ್ಲ. ನಾವು ವೈಜ್ಞಾನಿಕ ಮನೋಭಾವದಿಂದ ಎಲ್ಲ ರಂಗಗಳನ್ನ ಪರಿಶೋಧಿಸುತ್ತಿದ್ರೆ ನಮ್ಮ ಕೇಡು ತಪ್ಪದು ಎಂದು ಎಚ್ಚರಿಸಿದ್ದಾರೆ. ವಿಜ್ಞಾನ ದಿನಾಚರಣೆಯ ಸಂದರ್ಭದಲ್ಲಿ ರಾಷ್ಟ್ರಕವಿಗಳ ಮಾತು ಹೆಚ್ಚಿನ ಮಹತ್ವವನ್ನ ಪಡೆದುಕೊಳ್ಳುತ್ತೆ ಅಂತ ಹೇಳ್ತಾ ಈಗ ತಮ್ಮೆಲ್ಲರ ಸಮಕ್ಷ ನಾಡಗೀತೆಯನ್ನ ಪ್ರಸ್ತುತಪಡಿಸಲಾಗುವುದು. ಈ ಸಂದರ್ಭದಲ್ಲಿ ಸಭಾಸದರು ಎದ್ದು ನಿಲ್ಬೇಕಾಗಿ
भारत जननीय तनुजाते जय हे कर्नाटक माते, जय सुंदर नदी वनಗಳ ನಾಡಿ, जय हे ರಸ ಋಷಿಗಳ ಬೀಡೆ. ಭೂದೇವಿಯ ಮುಡದ ನವಮಣಿಯೇ, ಗಂಧದ ಚಂದನ ಹೊಂದಿನ ಗಣಿಯೇ, ರಾಘವ ಮಧುಸೂದನರವತರಿಸಿದ ಭಾರತ ಜನನಿಯ ತನುಜಾತೆ. ಜನನಿಯ ಜೋಗುಳ ವೇದದ ಘೋಷ, ಜನನಿಗೆ ಜೀವವು ನಿನ್ನಾವೇಶ. ಹಸುರಿನ ಗಿರಿಗಳ ಸಾಲೆ, ನಿನ್ನಯ ಕೊರಳಿನ ಮಾಲೆ. ಕಪಿಲ ಪತಂಜಲ ಗೌತಮ ಜಿನನುತ ಭಾರತ ಜನನಿಯ ತನುಜಾತೆ ಶಂಕರನ ಮನುಜ ವಿದ್ಯಾರಣ್ಯ ಬಸವೇಶ್ವರ ಮನ್ಮರ ದಿವ್ಯಾರಣ್ಯ ತನ್ನ ಷಡಕ್ಷರಿ ಕೊಂಡ ಪಂಪನ ಭೂಮಿ ಮತಿ ಜನ್ನ ಕುಮಾರ ವ್ಯಾಸರ ಮಂಗಳ ಧಾಮ ಕವಿ ಕೋಗಿಲೆಗಳ ಪುಣ್ಯಾರಾಮ ನಾನಕರಮಾನಂದ ಕಬೀರರ ಭಾರತ ಜನನಿಯ ತನುಜಾತೆ ಡಂಕಣ ಜಗಣರ ನೆಚ್ಚಿನ ಬೀಡೆ ಕೃಷ್ಣ ಶರಾವತಿ ತುಂಗ ಕಾವೇರಿಯ ವರರಂಗ ಚೈತನ್ಯ ಪರಮಹಂಸ ವಿವೇಕರ ಭಾರತ ಜನನಿಯ ತನುಜಾತೆ ಸರ್ವಜನಾಗಡ ಶಾಂತಿಯ ತೋಟ ರಸಿಕರ ಕಂಗಳ ಸೆಳೆಯುವ ನೋಟ ಹಿಂದೂ ಕ್ರೈಸ್ತ ಮುಸಲ್ಮಾನ ಪಾರಸಿಕ ಜೈನರುದ್ಯಾನ ಜನಗಣ ಹೋಲುವ ದೊರೆಗಳ ಧಾಮ ಕಾಯಕ ವೈಣಿಕರ ರಾಮ ಕನ್ನಡ ನುಡಿ ಕುಣಿದಾಡುವ ದೇವ ಕನ್ನಡ ತಾರಿಯ ಮಕ್ಕಳ ದೇವ ಭಾರತ ಜನನಿಯ ತನುಜಾತೆ ಜಯ ಹೇ ಕರ್ನಾಟಕ ಮಾತೆ ಜಯ ಹೇ ಕರ್ನಾಟಕ ಮಾತೆ ಜಯ ಹೇ ಕರ್ನಾಟಕ ಮಾತೆ.
ಹಾಗೂ ನಾಡಗೀತೆಯನ್ನ ನೆರವೇರಿಸಿದ ಕುಮಾರಿ ಕಲ್ಯಾಣಿ, ಕುಮಾರಿ ಅಲೀಶಾ, ಕುಮಾರಿ ಶೋಭಾ ಮತ್ತು ಕುಮಾರಿ ಅನ್ಸಿಲಾ ಅವರಿಗೆ ಧನ್ಯವಾದಗಳು. ಬಂಧುಗಳೇ, ಈ ಸಾಲಿನಿಂದ ಕರ್ನಾಟಕ ಘನ ಸರ್ಕಾರವು ರಾಷ್ಟ್ರೀಯ ವಿಜ್ಞಾನ ದಿನಾಚರಣೆ ಅಂಗವಾಗಿ ಪ್ರತಿಜ್ಞೆಯೊಂದನ್ನ ನಾವು ಸ್ವೀಕಾರ ಮಾಡಬೇಕು ಅಂತ ಫರ್ಮಾನ್ ಹೊರಡಿಸಿದೆ. ನಾನು ಪ್ರತಿಜ್ಞಾ ವಿಧಿಯನ್ನ ಬೋಧಿಸ್ತೀನಿ. ತಾವು ಎದ್ದು ನಿಂತು ಬಲಗೈಯನ್ನ ಮುಂದೆ ಚಾಚಿ ನಾನು ಹೇಳಿದಂತೆ ಪುನರುಚ್ಚರಿಸಬೇಕಾಗಿ ವಿನಂತಿಸ್ತೀನಿ. ಪ್ರತಿಜ್ಞಾ ವಿಧಿಯನ್ನ ಮಾನ್ಯ ಗೃಹ ಸಚಿವರು ಬೋಧಿಸುತ್ತಿದ್ದಾರೆ.
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. ಪ್ರತಿಜ್ಞಾ ವಿಧಿ. ನಾನು ಭಾರತೀಯ ಸಂವಿಧಾನದ 51A(H) ವಿಧಿಯ ಅನ್ವಯ ವೈಜ್ಞಾನಿಕ ಮನೋಭಾವನೆ ಮತ್ತು ವೈಚಾರಿಕತೆಯನ್ನು ಬೆಳೆಸಿಕೊಳ್ಳುತ್ತೇನೆ. ನಾನು ಪ್ರಶ್ನೆ ಮಾಡದೆ ಯಾವುದೇ ತರ್ಕವನ್ನು ಒಪ್ಪುವುದಿಲ್ಲ ಹಾಗೂ ಸಂವಿಧಾನದ ಮೂಲಭೂತ ಕರ್ತವ್ಯದ ಆಶಯದಂತೆ ಮೌಢ್ಯತೆ ಮತ್ತು ಅಂಧಕಾರವನ್ನು ನಿರ್ಮೂಲನೆ ಮಾಡಿ ಜೀವ ಜಗತ್ತಿಗೆ ಪೂರಕವಾದ ಬದುಕನ್ನು ರೂಪಿಸಿಕೊಳ್ಳುತ್ತೇನೆಂದು ಈ ಮೂಲಕ ರಾಷ್ಟ್ರೀಯ ವಿಜ್ಞಾನ ದಿನದಂದು ಪ್ರತಿಜ್ಞೆ ಮಾಡುತ್ತೇನೆ. ಜೈ ಭಾರತ್, ಜೈ ಕರ್ನಾಟಕ, ಜೈ ಸಂವಿಧಾನ, ಜೈ ವಿಜ್ಞಾನ. ಥ್ಯಾಂಕ್ ಯು.
ಧನ್ಯವಾದಗಳು. Ladies and gentlemen, it's our distinct honor to gather here today in the esteemed presence of Professor N.K. Loknath, the 26th Vice Chancellor of our university. Professor Loknath's remarkable career as a physicist, researcher, educator, and administrator has left an everlasting impression on the academic landscape. However, Professor Loknath's impact transcends academia. His outstanding administrative acumen has been instrumental in shaping the University of Mysore's trajectory. Without further ado, I respectfully invite our Honorable Vice Chancellor to deliver the welcome address.
ಎಲ್ಲರಿಗೂ ನನ್ನ ನಮಸ್ಕಾರಗಳು. ಮೈಸೂರು ವಿಶ್ವವಿದ್ಯಾಲಯದ ಎಲ್ಲ ಅಧಿಕಾರಿ ವರ್ಗದವರೇ, ಮಾನ್ಯ ಸಿಂಡಿಕೇಟ್ ಹಾಗೂ ಶಿಕ್ಷಣ ಮಂಡಳಿ ಸದಸ್ಯರುಗಳೇ, ಎಲ್ಲಾ ನಿಲಯದ ಡೀನರ್ಗಳೇ, ಬೋಧಕ ವರ್ಗ ಹಾಗೂ ಬೋಧಕೇತರ ವರ್ಗದವರೇ, ವಿದ್ಯಾರ್ಥಿಗಳೇ, ಸಂಶೋಧಕರುಗಳೇ, ವಿದ್ವಾಂಸರೇ, ಮಾಧ್ಯಮ ಮಿತ್ರರೇ, ತಮಗೆಲ್ಲ ರಾಷ್ಟ್ರೀಯ ವಿಜ್ಞಾನ ದಿನದ ಶುಭಕಾಮನೆಗಳು. Before introduce our honored guest, Dr. Radhakrishna, let me talk about a minute about the significance of Science Day. As you all aware that National Science Day is celebrated in India every year on 28th February. This day commemorates the invention of the Raman effect by the great Indian physicist Sir Chandrasekhar Venkata Raman. It was on this day in 1928 that Sir C.V. Raman made his discovery. He was awarded the Nobel Prize in 1930 in physics for his great success in the field of physical sciences. Raman effect is nothing but the scattering of light when passing through different materials. This day is celebrated as a science carnival, recognizing the scientific activities and programs in the country through the participation of students from schools and colleges, along with scientists across India. The main objectives of celebrating this National Science Day is to bring awareness to people about the importance of scientific applications in their daily life and to encourage them by popularizing science and technology. Also, Science Day aims to inspire students, particularly young minds, to take up science as a career, which led to a scientific research. In turn, it encourages innovations, experimentation, and exploration in various scientific fields. Let us remember the great scientist Sir C.V. Raman, who made us proud by winning the Nobel Prize for Physics nearly 100 years ago. It reflects on the lack of priority that we have not been able to produce another Nobel Prize in Physics or any other subject during the 95 years. Winning a Nobel Prize is very, very important because it boosts scientific temper, besides enhancing our image among the nations. Let us hope our leaders keep this in mind and allocate funds generously for scientific research so that we can prove to the world that we are second to none in the field. As you all aware that every year Science Day will be given in a theme. So this year, the theme for National Science Day 2025 is Empowering Indian Youth for Global Leadership in Science and Innovation for Viksit Bharat. So this theme emphasizes the role of young minds in advancing India's scientific and technological progress, which underlines the importance of innovation and leadership for the country's development. With this small background of the National Science Day 2025, let me turn my attention to briefly introduce our chief guest, Dr. Radhakrishna, who has kindly agreed to deliver the National Science Day speech for 2025. Dr. Radhakrishna is currently serving as head Instrumentation Division of Space Astronomy Group, URO Satellite Center, Indian Space Research Organization, ISRO, Bengaluru. He completed MSc in Physics from Bangalore University and received his PhD from Indian Institute of Science, Bengaluru, in the area of Applied Physics and Instrumentation in the year 2003. Dr. Radhakrishna was a postdoctoral fellow, followed by research scientist at Toyohashi University of Technology, Japan, between 2003 and 2007. Since 2007, he has been at the Space Astronomy Group of URO Satellite Center, ISRO Bangalore, as scientist. His research area mainly focuses on ionizing radiation detector physics and instrumentation. After joining ISRO, he is leading the team in configuring and developing instruments for space science mission. Dr. Radhakrishna was principal investigator for Chandrayaan-2 large areas of X-ray spectrometer known as class payload, which is on Chandrayaan-2 orbiter successfully orbiting on lunar orbit since September 2019. For this work, this team was awarded by Astronomical Society of India with Zubin Kembawi Award in the year 2024. As a head of the division, he has guided the team in building payloads for Aditya L1 and Chandrayaan-3 missions. He is also leading the development activities of future instruments like X-ray polarimeter, X-ray optics for space astronomy missions. He has successfully guided several students to their PhD degree and has published more than 50 articles in international journals. And he has delivered several lectures as a sciences as a part of the outreach program in ISRO. Ladies and gentlemen, we have in our midst such a distinguished speaker. Please join me in welcoming Dr. Radhakrishna, who is going to deliver the speech on space science missions, challenges and opportunities. I take this opportunity to welcome you, sir. I also welcome our registrar Srimati Savita, all the officers, all the invitees, syndicate and academic council members, deans, faculty and non-teaching staff, research students, and the media persons. Thank you one and all. Jai Hind, Jai Karnataka.
ಎಲ್ಲರನ್ನ ಹೃತ್ಪೂರ್ವಕವಾಗಿ ಸ್ವಾಗತಿಸಿ ಪ್ರಾಸ್ತಾವಿಕ ನುಡಿಗಳನ್ನಾಡಿದ ಗೌರವಾನ್ವಿತ ಕುಲಪತಿಗಳು ಕೂಡ ತಮ್ಮೆಲ್ಲರ ಪರವಾಗಿ ಆತ್ಮೀಯವಾದ ಸ್ವಾಗತವನ್ನ ಬಯಸ್ತೀನಿ. ಮಾನ್ಯ ಕುಲ ಸಚಿವರು ಸನ್ಮಾನ್ಯ ಕುಲಪತಿಗಳಿಗೆ ಪುಷ್ಪಗುಚ್ಛವನ್ನ ನೀಡಬೇಕಾಗಿ ವಿನಂತಿಸ್ತೀನಿ. ಈ ಸಂದರ್ಭದಲ್ಲಿ ನಮ್ಮೊಂದಿಗೆ ಉಪಸ್ಥಿತರಿರುವ ಮಾನ್ಯ ಕುಲಸಚಿವರಾದ ಶ್ರೀಮತಿ ಎಂ.ಕೆ. ಸವಿತಾ ಮೇಡಮ್ ಅವರು ಕೂಡ ತಮ್ಮೆಲ್ಲರ ಪರವಾಗಿ ಪ್ರೀತಿಪೂರ್ವಕ ಸ್ವಾಗತ. ಕುವೆಂಪು ಕನ್ನಡ ಸಂಸ್ಥೆ ನಿರ್ದೇಶಕರು ಅವರಿಗೆ ಪುಷ್ಪಗುಚ್ಛವನ್ನ ನೀಡಬೇಕಾಗಿ. ಈ ಸಂದರ್ಭದಲ್ಲಿ ವಿವಿಧ ಕಾಲೇಜುಗಳಿಂದ ಬಂದಿರೋ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ NSS ಸ್ವಯಂ ಸೇವಕರು ಕೂಡ ಅತ್ಯಂತ ಪ್ರೀತಿಪೂರ್ವಕ ಸ್ವಾಗತವನ್ನ ಕೋರ್ತೀನಿ. ಬಂಧುಗಳೇ, 1924ರಲ್ಲಿ ಕಲ್ಕತ್ತಾ ವಿಶ್ವವಿದ್ಯಾಲಯದ ಸಮಾರಂಭವೊಂದರಲ್ಲಿ ಸರ್ ಸಿ.ವಿ. ರಾಮನ್ ಅವರು ಮುಖ್ಯ ಅತಿಥಿಗಳಾಗಿ ಭಾಗವಹಿಸಿರ್ತಾರೆ. ಕೆಲವು ದಿನಗಳ ಹಿಂದಷ್ಟೇ ಅವರಿಗೆ ಲಂಡನ್ನ ರಾಯಲ್ ಸೊಸೈಟಿಯಿಂದ ಪ್ರತಿಷ್ಠಿತ ಫೆಲೋಶಿಪ್ ದೊರೆತಿರುತ್ತೆ. ಆ ಸಮಾರಂಭದಲ್ಲಿ ಈ ವಿಷಯವನ್ನ ಪ್ರಸ್ತಾಪಿಸಿ ಆಯೋಜಕರು ಅವರನ್ನ ಅಭಿನಂದಿಸ್ತಾರೆ. ಆಗ ರಾಮನ್ ಅವರು ಮಾತನಾಡ್ತಾ, ಈ ಫೆಲೋಶಿಪ್ ಎಲ್ಲ ಬಹಳ ಚಿಕ್ಕ ವಿಷಯ, ನನ್ನ ಗುರಿ ಏನಿದ್ರು ನೋಬೆಲ್ ಪ್ರಶಸ್ತಿ ಪಡೆಯುವಂತ, ನೋಡ್ತಾ ಇರಿ 5 ವರ್ಷದಲ್ಲಿ ನೋಬೆಲ್ ಪಡೆದೇ ಇರ್ತೀನಿ ಅಂತ ಹೇಳ್ತಾರೆ. ಸರಿಯಾಗಿ ಅದಕ್ಕೆ 5 ವರ್ಷಕ್ಕೆ ಅವರಿಗೆ ನೋಬೆಲ್ ಪ್ರಶಸ್ತಿ 1930ರಲ್ಲಿ ದೊರೆಯುತ್ತೆ. ಇನ್ನೊಂದು ಆಶ್ಚರ್ಯದ ಸಂಗತಿ ನಿಮ್ಗೆ ಹೇಳ್ತೀನಿ. ಪ್ರತಿ ವರ್ಷದ ಕೊನೆಯಲ್ಲಿ ಡಿಸೆಂಬರ್ ತಿಂಗಳಲ್ಲಿ ನೋಬೆಲ್ ಪ್ರಶಸ್ತಿ ಪುರಸ್ಕೃತರ ಪಟ್ಟಿ ಘೋಷಣೆ ಆಗುತ್ತೆ. ಸ್ವೀಡನ್ ನಲ್ಲಿ ನಡೆಯುವ ಈ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಹಡಗಿನ ಮೂಲಕ ತಿಂಗಳ ಪ್ರವಾಸ ಮಾಡ್ಬೇಕಾಗುತ್ತೆ ಅಂತ ಹೇಳಿ 6 ತಿಂಗಳ ಮುಂಚೆ ಜುಲೈನಲ್ಲೇ 2 ಟಿಕೆಟ್ ಅನ್ನ, ಹಡಗಿನ ಟಿಕೆಟ್ ಅನ್ನ ಇವರು ಕಾದಿರ್ಸಿರ್ತಾರೆ. ಇನ್ನೂ ಪಟ್ಟಿನೇ ಘೋಷಣೆ ಆಗಿರಲ್ಲ, ಬಟ್ ನಮ್ಗೆ ಬಂದೇ ಬರುತ್ತೆ ಅನ್ನೋ ಒಂದು ಆತ್ಮವಿಶ್ವಾಸದಿಂದ ಅವರು ಟಿಕೆಟ್ ಅನ್ನ ಕಾದಿರ್ಸಿರ್ತಾರೆ. ಅದನ್ನ ತಮ್ಮ ಕೆಲಸದ ಬಗ್ಗೆ ಅವ್ರಿಗಿದ್ದಂತ ಕಾನ್ಫಿಡೆನ್ಸ್ ಮತ್ತು ಕ್ಲಾರಿಟಿ ತೋರಿಸುತ್ತೆ. ಇಂತ ಶ್ರೇಷ್ಠ ವಿಜ್ಞಾನ ಸಾಧನೆಯನ್ನು ಗುರುತಿಸುವ ಈ ವಿಜ್ಞಾನ ದಿನಾಚರಣೆಯನ್ನು ವಿದ್ಯುಕ್ತವಾಗಿ ಉದ್ಘಾಟಿಸಬೇಕಾಗಿ ವೇದಿಕೆ ಮೇಲಿನ ಗಣ್ಯರನ್ನ ವಿನಂತಿಸ್ತೇನೆ. ಬಂಧುಗಳೇ, 60ರ ದಶಕದಲ್ಲಿ ಭಾರತವು ಆಹಾರದ ಕೊರತೆಯನ್ನ ಎದುರಿಸ್ತಾ ಇತ್ತು. ಅಮೆರಿಕದಿಂದ ದವಸ ಧಾನ್ಯವನ್ನ ಭಾರತಕ್ಕೆ ಒದಗಿಸಲಾಗ್ತಾ ಇತ್ತು. ಅಂದು ತನ್ನ ಪ್ರಜೆಗಳಿಗೆ ಸಾಕಾಗುವಷ್ಟು ಆಹಾರ ಉತ್ಪಾದನೆ ಮಾಡುವಲ್ಲಿ ಕಷ್ಟಪಡುತ್ತಿದ್ದ ನಮ್ಮ ದೇಶ ಇಂದು ದೇಸಿ ತಂತ್ರಜ್ಞಾನದ ಮುಖೇನ ರಾಕೆಟ್ ಮತ್ತು ಉಪಗ್ರಹಗಳನ್ನು ನಿರ್ಮಿಸಿ ಬಾಹ್ಯಾಕಾಶದಲ್ಲಿ ಹೊಸ ಭಾಷ್ಯವನ್ನ ಬರೀತಾ ಇದೆ. ಸ್ಪೇಸ್ ಸೈನ್ಸ್ ಕ್ಷೇತ್ರದಲ್ಲಿ ಭಾರತೀಯರ ಸಾಧನೆಯನ್ನ ಸುವರ್ಣಾಕ್ಷರಗಳಲ್ಲಿ ಬರೆದಿಡಬೇಕು. ಸೈಕಲ್ ಮತ್ತು ಎತ್ತಿನ ಬಂಡಿಗಳ ಮೇಲೆ ರಾಕೆಟ್ ನ ಭಾಗಗಳನ್ನ ಸಾಗಿಸುವ ಆರಂಭಿಕ ದಿನದಿಂದ ಚಂದ್ರಯಾನ 3ರವರೆಗೆ ಇಸ್ರೋ ಸಂಸ್ಥೆ ಸುದೀರ್ಘ ಯಾತ್ರೆಯನ್ನ ಕ್ರಮಿಸಿದೆ. ದಿವಂಗತ ವಿಕ್ರಮ್ ಸಾರಾಭಾಯ್, ಸತೀಶ್ ಧವನ್, UR ರಾವ್ ಮುಂತಾದ ಮೇಧಾವಿ ವಿಜ್ಞಾನಿಗಳು ಇಂದು ಭಾರತವನ್ನ ಜಾಗತಿಕ ಭೂಪಟದಲ್ಲಿ ತಲೆ ಎತ್ತಿ ನಿಲ್ಲುವಂತೆ ಮಾಡಿದ್ದಾರೆ. ಈ ಶ್ರೇಷ್ಠ ವಿಜ್ಞಾನಿಗಳು ಹಾಕಿಕೊಟ್ಟ ಪರಂಪರೆಯ ಸಮರ್ಥ ವಾರಸುದಾರರಾಗಿ ಕನ್ನಡಿಗರೇ ಆದ ಡಾಕ್ಟರ್ ರಾಧಾಕೃಷ್ಣ ಅವರು ನಮಗೆ ಗೋಚರಿಸ್ತಾರೆ. ಈಗ ಶ್ರೀಯುತರು ಸ್ಪೇಸ್ ಸೈನ್ಸ್ ಮಿಷನ್ ಚಾಲೆಂಜಸ್ ಅಂಡ್ ಆಪರ್ಚುನಿಟೀಸ್ ಎಂಬ ವಿಷಯವನ್ನು ಕುರಿತು ಉಪನ್ಯಾಸವನ್ನ ನೀಡಬೇಕಾಗಿ ವಿನಂತಿಸುತ್ತೇನೆ. ಗುಡ್ ಮಾರ್ನಿಂಗ್ ಎಲ್ರಿಗೂ. ಮೊದಲನೇದಾಗಿ ರೆಸ್ಪೆಕ್ಟೆಡ್ ವೈಸ್ ಚಾನ್ಸಲರ್ ಪ್ರೊಫೆಸರ್ ಲೋಕನಾಥ್ ಅವರು ನಮಗೆ ಇಲ್ಲಿ ಕರೆಸಿ ಈ ಅಪರ್ಚುನಿಟಿ ಕೊಟ್ಟಿದ್ದಕ್ಕೆ ಅವರಿಗೆ ಮೊದಲನೇ ಧನ್ಯವಾದಗಳು. ಹಾಗೂ ಅವರ ತಂಡಕ್ಕೆ, ಅಡ್ಮಿನಿಸ್ಟ್ರೇಟಿವ್ ಮತ್ತು ಎಲ್ಲ ಫ್ಯಾಕಲ್ಟಿಗಳಿಗೆ ನನ್ನ ವಂದನೆಗಳು. ಮತ್ತೆ ಇಲ್ಲಿ ಬಂದಿರುವಂತಹ ಎಲ್ಲ ಜೂನಿಯರು ಮತ್ತು ವಿದ್ಯಾರ್ಥಿನಿಯರಿಗೆ ಸ್ಪೇಸ್ ಸೈನ್ಸ್ ದಿನಾಚರಣೆಯ ಅಂಗವಾಗಿ ಶುಭಾಶಯಗಳು ಹಾಗೂ ನಿಮಗೆಲ್ಲರಿಗೂ ಸ್ವಾಗತ. ಇಂದಿನ ಈ ಸಂದರ್ಭದಲ್ಲಿ the topic which I discussed with the professor, which I will be talking is on space science missions, challenges and opportunities. ಇವತ್ತು ಈಗಾಗಲೇ ನಿಮ್ಗೆಲ್ಲ ಗೊತ್ತಿರುವಂಗೆ ನ್ಯಾಷನಲ್ ಸೈನ್ಸ್ ಡೇ to commemorate the discovery of Raman effect by Professor C.V. Raman. ನಮ್ಗೆ ನಾವೆಲ್ಲ ಪ್ರೌಡ್ ಆಗಿ ಹೇಳ್ಬೋದು, ಇಂಡಿಯನ್ ಡಿಸ್ಕವರ್ಡ್ ಒನ್ ವೆರಿ ಗ್ರೇಟ್ ಫಿನಾಮಿನಾ ಇನ್ ಫಿಸಿಕ್ಸ್. ಎಸ್, ಡಿಸ್ಕವರಿ ಹ್ಯಾಸ್ ಹ್ಯಾಪನ್ಡ್. ಬಟ್ ನಿಮ್ಗೆ ಗೊತ್ತಿರುವ ಹಾಗೆ, ಎಸ್ಪೆಷಲಿ ಸ್ಟೂಡೆಂಟ್ಸ್ ಗಳಿಗೆ ನಾನೊಂದು ಹೇಳ್ತಾ ಇರೋದೇನಂದ್ರೆ, ಇದರ ಇಂಪ್ಯಾಕ್ಟ್, ನೊಬೆಲ್ ಅವಾರ್ಡ್ ಬರ್ಬೇಕಿದ್ರೆ ಅಂತ ಇಂಪ್ಯಾಕ್ಟ್ ಇದ್ರೆ ಮಾತ್ರ ನೊಬೆಲ್ ಅವಾರ್ಡ್ ಬರಬೇಕು. ಆ ರಾಮನ್ ಇಫೆಕ್ಟಿನ ಇಂಪ್ಯಾಕ್ಟ್ ಏನು ಅಂತ ಇಂದಿನ ಆಧುನಿಕ ಎಲ್ಲಾ ಕ್ಷೇತ್ರಗಳಲ್ಲಿಯೂ ಏನಾಗಿದೆ ಅಂತ ಬಹುಶಃ ನೀವೆಲ್ಲ ಸ್ವಲ್ಪ ನೋಡ್ಕೊಂಡ್ರೆ ಚೆನ್ನಾಗಿರುತ್ತೆ. ನಾನು ಯಾಕೆ ಇದನ್ನು ಹೇಳ್ತಾ ಇದ್ದೀನಿ ಅಂದ್ರೆ, ಪ್ರೊಫೆಸರ್ ರಾಮನ್ ಡಿಸ್ಕವರ್ಡ್, ಬಟ್ ಇಟ್ ವಾಸ್ ಫಾಲೋಡ್ ಅಪ್ by lot of innovations. So ಈ ಡಿಸ್ಕವರಿ ಇಂದ ಇನೋವೇಷನ್ ಮಾಡಿ ಇವತ್ತು, ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ರಾಮನ್ ಸ್ಪೆಕ್ಟ್ರೋಮೀಟರ್ ಅಂತ ಯು ಹ್ಯಾವ್ ಪ್ರಾಡಕ್ಟ್ ರಾಮನ್ ಸ್ಪೆಕ್ಟ್ರೋಮೀಟರ್. ಯಾರು ಇದನ್ನೆಲ್ಲ ಮಾಡ್ತಾ ಇರೋದು? ಇನ್ಯಾರೋ ಮಾಡ್ತಾ ಇದ್ದಾರೆ. ಸೊ ರಾಮನ್ ಸ್ಪೆಕ್ಟ್ರೋಮೀಟರ್ಸ್, ಇಟ್ ಹ್ಯಾಸ್ ಟಚ್ಡ್ ಆಲ್ ಆಸ್ಪೆಕ್ಟ್ಸ್ ಆಫ್ ಸೈನ್ಸ್ ಅಂಡ್ ಟೆಕ್ನಾಲಜಿ. Even we are using Raman spectrometer in space also. Planetary exploration ಗೆ Raman spectrometer use ಮಾಡ್ತೀವಿ. But all these laboratory Raman spectrometer, laser Raman spectrometer, ಇದನ್ನೆಲ್ಲ innovative discovery, the concept ಅನ್ನು innovation ಆಗಿ ಯೂಸ್ ಮಾಡಿ ಅದರಿಂದ ಪ್ರಾಡಕ್ಟ್ ಅನ್ನೋರು ಇನ್ಯಾರು? ಸೊ ಈ ಗ್ಯಾಪ್ ನಮ್ಮ ಪ್ರೊಫೆಸರ್ ಅವರು, ವೈಸ್ ಚಾನ್ಸಲರ್ ಅವರು ಆಲ್ರೆಡಿ ಟಚ್ಡ್ ಅಪಾನ್. ಆಮೇಲೆ ನೋ ನೊಬೆಲ್ ಅವಾರ್ಡ್ ಹ್ಯಾಸ್ ಬೀನ್ Nobel awardee is produced by India. But even what was lacking is also innovation. So even a lot of innovations are happening, no doubt about that. But these hardcore, very significant innovations are yet to come from our.
So Raman effect has touched the technology based on this is now ubiquitous, you can say. It is there in every aspect of every aspect of research areas, fields, including, as I said, space. So coming to the topic, I will not be discussing about the impact of Raman effect, but I call upon all the students, especially the BSc, MSc students, to look into where and all it is used. Then you will know the significance of such discoveries and the inventions required to bring the discovery into the useful applications. And space science missions, challenges and opportunities. As you know, wherever there is challenge, there is opportunity. So I'm not putting it as this is a challenge, this is the opportunity. But as we discuss, you will know, okay, these are the challenges, these are the opportunity, you will figure it out. And the topic is vast, just like space, which is vast, the topic is also very vast. So I will touch upon a few things, hopefully, which will inspire you. And what I will cover is the history of space science, where it has come from, and where we are now. What are the big science missions? ಮತ್ತೆ ISRO, what is that we have done? Some of these things we will discuss. And I will try to cover in about 45 minutes, followed by maybe discussions. Hopefully, I will be able to complete in 45 minutes. So, coming to the topic, I'm sure many of you have heard of many science missions. You talk about, the international missions. Recently, all of you have heard of James Webb Telescope. And Indian missions, obviously, you all know the Chandrayans, the Astrosat. How many of you have heard of Astrosat? Astrosat. It's a big astronomy mission by India. 10 years. It is even today, it is in the orbit, giving a lot of data for astrophysicists in India. People are analyzing this data. We'll come to that. But I am sure you are able to see these slides through the display here. And you can see the list of, will not look into what are those, each of those, list of missions, many missions by internationals. Only big missions I have put here. You have invisible, infrared, ultraviolet missions, X-ray missions, gamma ray missions, in microwave, in radio. Many missions, many satellites have been sent to space. And the one in blue, Astrosat and Exposat, are astronomy missions from India. You will see them a little later. And then there are solar missions to study sun. So there are many missions, India's solar missions. So is it okay, a little bit interactive? Okay, India's solar mission, Aditya, and then planetary missions to study the solar system planets. We have Chandrayaan 1, 2, 3, and Mars orbiter mission, Mangalyaan. And then deep space mission by NASA, for example, Voyager, which has crossed, even today is going on, 30 plus years, close to 40 years. It is going, still traveling beyond solar system. And the countries which are doing, we have NASA, like US agency, ESA, European Space Agency, JAXA, Japanese Space Agency, Roscosmos, Russian, ISRO, and Chinese Space Agency. These are the agencies which are involved with these missions. And two things I want to tell here. There is a Hubble Space Telescope. How many of you know about Hubble? Just raise hand. I will not ask any questions, but yeah. You should read about Hubble Space Telescope. It's like, greatest instrument. It's considered as one of the greatest instruments built by human beings. We'll see why it is. And it is there in the orbit for the past 30 years. It is in the orbit. And why servicing missions happen? Astronauts have gone to space and serviced them. That is the kind of mission it is. And JWST, they spent about 140 lakh crores. 140 lakh crores. And 20 years to build. So why people spend such amount of money? We go to space, look at various things and tell that there is a star, that this happened, that happened. Why they do that? That is the spirit of scientific inquiry. And the human being, the basic instinct, one of the basic instincts of the human being is curiosity and the exploration, curiosity to explore. Look at this card, the caveman. He looks at the sky and thinks, where did it all come from? And today's scientist sitting in the laboratory, he also wonders, where did it all come from? What has changed from that to this? Now we know a lot about our universe, the physical universe, and we understood many things. It's all through this kind of space mission. In fact, the caveman, why I'm saying is, even there are a lot of drawings in some of the oldest caves depicting the events happened in sky. And even in India, there is a cave in Kashmir, and where they found, people drawing some events happened in the sky that time. They found out that exactly somewhere around 5,000 years back, there was an explosion, supernova. The star exploded, and it was looking like a bright sun. So they put two sun and the moon, etc. And they have. So that means that curiosity is always there. So it is the pursuit of that which makes us to evolve. And today what we are today is because of these kind of curiosity. So it is very important once again as part of National Science Day. And in fact, we have this year they introduced this oath taking. And it's very important we have that spirit of inquiry and also the curiosity. We have to nurture that. So unfortunately, we have a lot of distractions these days. But without falling into that, we have to nurture that. That is why we are taking oath, and then only probably we will live better and better tomorrow for the next generations. And the curiosity, and when you talk about space and the universe, entire questions, all that what we have, we can bring down to these three questions. What is the origin of the universe? I am sure all of you thought how all these things have come, when it has come. And the laws governing the universe, which we are trying to understand. Laws governing how the stars are made, how they produce energy, how the solids have come, how the material is produced, and all these things, how it is governed, the laws which govern this universe, and the ultimate fate of the universe. Obviously, you all will think what will happen tomorrow, right? So this is what, entire all aspects can be brought down to these three fundamental questions. So our pursuit is to understand this, and then from this, we have motivation to go into space, and that's how the space science is born. And the motivation, little more on motivation, understanding the origin of the universe, like, the Big Bang theory, the universe started with a Big Bang. So that theory and evolution of the universe is one of the questions we now want to understand. And then there are a lot of exotic things like dark matter, dark energy. We want to understand these things. And you would have heard of Kappu Kuligalu, black holes, neutron stars. These are all exotic objects in the sky, and we want to understand them. And searching for life beyond Earth. So don't we think, we always get this question, is there life elsewhere? Whether Earth, when there are billions of stars, billions of galaxies, why Earth, only this Earth has life? Or whether it is true that only we are here. So we want to know whether there is life beyond Earth. So that's a very, it's presently in space, and one of the hot topic is that. And if there is life, then you see the thinking what we have. Entire our perception, our thinking will change. So that is that. Then of course, exploring our own system, how Earth is created, and that is linked to life, how the solar system is created. These are basically the questions. All the missions, I talked about many missions, and with many billions of dollars, James Webb Telescope, about 140 lakh crores. Imagine the amount they spend. So these are the questions we want to answer. But in the process, we developed a lot of technology which impacts other aspects of life, which we will see a little later. And whole thing starts with Galileo. You imagine, you know about Galileo's story. I think you all should read story of Galileo, because in spite of that is the kind of time he was in, where it was not allowed to, think beyond what you are asked to believe. And he looked at the sky, risking his life. He looked at the sky using telescope, and he sees four moons of Jupiter. And in fact, that's why Galileo is called father of modern astronomy. In fact, he's called as father of modern science, because that has changed. That particular observation of him has changed entire aspect. Today, we are able to launch satellite because it is Galileo who has seen the moons going around Jupiter. Obviously, the question comes how they go around. So then comes Kepler, Newton, and rest of the people, Tycho Brahe. They all come and study more and more of that and bring out how the planets move around the sun, the laws of planetary motions, Kepler's laws, and Newton says why they stay there, why they don't fall or they don't run away. So all these things have been answered after Galileo, who has done that first observation using telescope. Why I am highlighting this is, it is some such people who chase their, I want to know whatever it is. That is what drives this society in every field, in fact, for that matter. But same is the case here. And he does many other things. And the major impactful thing is one of the discoveries is Jupiter's moons. And since then, we know many objects in the sky. We know sun and solar system. We know celestial objects like many stars, the galaxies, the nebula. Will not, try to understand each of these, but a lot of exotic objects. And then there are black holes, neutron stars, and the brightest objects, the supermassive black hole and active galactic nuclei, the center of galaxy, which is many galaxies are there. Some of the galaxies have supermassive black holes with emitting intense amount of energy. So these are the many aspects which we know that there are these kind of things we understand, many things we understand, many things we don't understand, and it is the study of these is what is driving space astronomy. However, all these things can be studied from ground also. Ground, you can build larger and larger telescope. But all these telescopes are in mountain regions, etc., because you don't want any pollution, air pollution or light pollution. So you go to mountain region. Now, question is, if we can build big telescopes on ground, why we have to spend so much of millions of rupees, billions of rupees, and go to space? Because there are two things which hinder us. One is atmospheric effect. You know, the stars twinkle. Twinkling star is due to the atmospheric effect, and it's the basic, our high school experiment, the refraction experiment, where things bend when you go from one medium to another medium. Like that, stars light, when as it reaches, because of the atmosphere density change, it keeps the bending changes as the atmosphere turbulence happens. So you see stars twinkle. So there are no, but otherwise stars don't twinkle. And another is, you all know that every body which has temperature emits radiation, right? Our body also emits radiation in infrared. So Earth emits radiation. So like that, every object emits radiation. The radiation we all will not survive. You know that, right? So if you want to study some objects which emit in X-rays, you have to go to space. Similarly, in visible light, although some wavelength is absorbed by the atmosphere, you know, every gas absorbs some light. So these are all high school physics and college physics. You learn that some characteristic energy is absorbed, something is emitted, depending on the temperature. So if you are on the ground, you will not be able to study fully. Similarly, some of the infrared also is absorbed by atmosphere. So if you want to study all the objects which are emitting different wavelength, you have to go to space. And see this example. There are two pictures here, same part of the sky. One is looking at optical light. Just if you see using your telescope or from ground, your eye can see only that much. But if you have an X-ray vision, you have an X-ray eye, you will see the next. So you see the number of objects which is around us. So that is the importance. And similarly, there is one object, if you pick crab. Crab is a nebula, it's a cloud of dust and gases. And center of it, there is a neutron star. Very fast spinning object is there. The same object, if you see in optical, you see one picture. If you see X-ray, if you see, you can see that neutron star structure because neutron stars emit in X-rays. Around that gas emits in other wavelength like optical, radio, far UV, etc. So the important thing is to go out and see for all these. If you don't go to the sky, you would not have known that crab is a neutron star. You can see that spinning star, jet, emission, etc. And there are many techniques. I'm not going to explain the techniques, but I want to assure you that, people say, oh, it is rocket science. It's very difficult. No. What you study in your, the classrooms, same thing is applied in all the experiments and techniques in space. It's all in how you understand your fundamentals, basics. Spectroscopy. You all do spectroscopy in the lab. These are used. Imaging, just taking photograph also used to study. And timing means you just keep collecting light, how the light changes, brightness changes. That you can do. And polarization, whether the light coming from there is polarized or not. These are the only experiments people do in astronomy. So whether it is in radio, whether it's in visible light, whether it's in X-rays, any wavelength you take, the experiments you do are only these four, which you all do in laboratories and to study different things in the lab. So this is my assurance. If you come to the space science studies, these are the things. Then of course you start applying physics and you start understanding what is happening based on the results what you get. Similarly, planetary science, if you go to planets, like Chandrayaan and that kind of planets, then you have different measurements to do. Like you have small sensors, you have geology study. It's not just the physicists who work here, and the geochemistry is another aspect, and you study magnetic field and particles, etc. So on and so forth. So these are the different techniques. And coming to the challenges, yes, these are simple techniques you explained, but what are the challenges? Obviously, you have to build very high sensitivity instruments. Sensitivity means, what you get from a distant object, which is billions of kilometers away, light years away. You want to have whatever you get, few photons, belakina kana by kana, photon by photon, it will be coming to you. So you have to collect each of those and make sense out of it, right? See, when you have a low light time, if you are operating cameraman, you can ask the camera person here, low light condition, he will change the aperture time. Means he will keep it for a little longer. Aperture is open for a little longer time so that you are collecting more light so that you can make sense out of what is coming. Similarly, you have to have a long observation and large aperture also. You know, big camera lens will be much more clarity, etc. Clarity is nothing but in the contrast based on the light what you see. So you have to build big telescope. You have to, collect for long time, and then there are a lot of other requirements. Like you have to put in a particular orbit, then only you can see. And instrument should be very stable. If your hand is shaky, you cannot take good photograph, right? Similarly, the telescope should be very stable platform. So that is the challenge. You have to build that kind of sensors and put in there. Then if there is any small jitter, it has to immediately correct it. So all these things are very important. Then of course, many other things like fuel efficiency and new technologies are coming. These are all challenges. And then there is radiation environment. In space, you have particle radiation, which can damage the instruments. So that radiation, it has to survive. You have to build the technology to survive that. And then the extreme temperatures, the space typical, the space is about 2 Kelvin, but typically you see 4 Kelvin temperature, deep space. But it goes through sun, no sun, multiple times satellite. So that time the temperature will go very high, very low. So it has to survive all this. So these are all challenges. Then distance and communication. The light takes, the light travels at about 3 lakh kilometers per second. That means it takes that much time to reach. Electromagnetic wave is nothing but that. Our mobile communication or radio wave, everything is electromagnetic. The speed is same, 3 lakh kilometers. So if you want to communicate, so if somebody is at 6 lakh kilometers and if you say hello, you will hear it after 2 seconds. So similarly, if the distance is much larger, it takes that much time. So you send a command here, it takes that much time. For example, Mangalyaan, we had that challenge. The communication takes few minutes, up to 20 minutes when the Mars is much farther. So how you have to consider all these. So if I suddenly send some command, suddenly, it will take that much time for satellite to get the command and say, okay, I will obey you, and send back the signal. It will take another 20 minutes. So you have to account for all this delay and plan your mission, build your instruments. Some automation should be there, some onboard intelligence. It senses itself and corrects. That is the kind of thing that we have to build. Deep space communication is a challenge. And then technology limitation, because, in science, always if somebody finds Raman has found Raman effect. Another person doing the same experiment, of course, he can do experiment and add more knowledge into that. But again, you will not discover the same thing. So you have to, if somebody has found something about some objects in the sky, you have to build a better instruments to find more or different things. So that means the technology, what is available today may not be sufficient. So you will need new technology. This is where a lot of innovation, lot of R&D goes. That is why James Webb Telescope has costed 140 lakh crore, simply because the technology required was not available. So you have entirely new technology. You even don't know whether you will be finally able to build that. So based on basic principles, they say, okay, it's possible, but these are the kind of effort required. So that's how you found. And so these are all challenges in space mission. And I'll skip these. The why sensitive required. So all these challenges you have to overcome and build a meaningful mission which can enhance our understanding of the universe and also technologically be advanced to the next level. Now, let's look at few missions. Some international missions and Indian missions. It's very important, we are all scientists. While we are proud of our own achievements and other things, it's very important we also get inspired by the other very great missions, very great instruments. And I touch upon some 4 great observatories of NASA. You will know why I am talking about that. So all these happened before 2000, before the year 2000. And you can see here, one is gamma, one is X-ray, one is visible, one is infrared. So it is covering large area of electromagnetic. spectrum. And again, I call upon all the students and space enthusiasts to look at the story of Hubble telescope. It's a very inspiring story, and a Hubble space nothing but a telescope, optical telescope, which is launched to space. It was launched in 1990, and it's a circular orbit, about 560 kilometers above the Earth. It is orbiting, even today, it is orbiting. And the weight of the satellite is about 11,000 kg. And it has optical, ultraviolet, near infrared, and diameter of the optics, 2.4 meter diameter. That is the kind of size, optics size. And you see the planning which has gone into this. While making the satellite and this telescope itself, I don't know, I did not understand how they thought about it, but they made it like we can repair it later if there is a problem. And unfortunately, immediately after the launch, when they looked at the picture, the photos which was taken by them, it was all blurry picture. And then they wondered, they looked at the entire history of making of the instrument. They realized that one of the mirror, you know, in the telescope, the lens and mirror quality of that is very, very important. One of the mirror was, figured. Figured means the mirror has to be perfect parabola, or whatever shape it is designed to. If it is even small deviation, will distort the image. That was wrongly made. So then they took edition, and in 1993, astronauts went into space and repaired the mirror. They changed the mirror and some of the other associated things. Look at the kind of thinking that has gone. You imagine the building of satellite, and again people going into space and repairing it. So that was repaired, and this is the result. If you see here, bottom left is before repair, right is after the repair. The image, you can see the image quality. And the above one is from the ground best image of that particular object. So you can see the importance of whole thing actually. So that is what Hubble has done. And it is not just that, in 30 years of life, it has shown us the universe like never before. Today, we all, you go to movie theater, you see anything, any of the animation, you will see beautiful galaxies and sky picture coming. Who gave this imagination? It is the Hubble telescope which has shown us the way different objects in the sky, the ultimate details, and that has told us what is there out in the space. And these are just some images. You can see it is called Butterfly Nebula, which is in the sky. You can see left and right image. Right is the Hubble image, right, for you. I mean, the clearer image is Hubble's image. And so this is another wonderful image there are many. You go to most of the pictures what you see are from Hubble. This image is very special because this is called baby picture of the universe. That is, we all, these days everybody has camera and phone. We take picture at every moment, every step we take picture and post it. And when the universe was just born, that is, as per the present understanding, 13.7 billion years old. And this picture is the picture taken just 300 million years after the universe is born. This concept is little, maybe difficult to understand initially, but if you know the thing that light started from that place at that time, that is just 300 million years after the Big Bang, and reached us today, because that is the distance. And so it gives the early universe, how it is. So this has inspired more missions. James Webb has come from Hubble, James Webb Telescope. And technologically, what was the challenge? If you want to collect that one photon coming and make sense of it, you have to collect it for many days. So this particular region, very small region of the sky, was monitored for 10 years at a different time, 10 years, and total cumulated time is 23 days. 23 days when you expose that small region, you get this region, this part of the sky. So we understand the universe much better. So similarly, heaviest satellite to look at very energetic phenomena in the sky, big what is that, explosions where gamma ray is emitted, was detected by Compton Gamma Ray Observatory. This was launched in 91. It's about 17,000 kg satellite. And right now it is deorbited and it has burnt out. And this is the image of the universe taken by that particular satellite. You can see there are a lot of gamma ray flashes in the sky, so which we understand now. Similarly, Chandra, another great Indian scientist, but he worked his major work, Nobel work. He is also Nobel winner. Subramaniam Chandrasekhar. He got Nobel Award for understanding what kind of stars become neutron stars and black holes. Because different sizes of stars, what kind of stars become neutron stars and black holes? That is the kind of work he has done. So the X-ray telescope built by NASA has been named as Chandra, the tribute given to Indian-born scientists, Indian-American scientists. So this is the image given by X-ray. This is called cosmic hand. It looks like, X-ray image of a hand. So cosmic hand. So like this, it has, I'm showing only pictures. I'm not talking about what it tells, all those things. We are not going into that. But the kind of inspiring pictures, which makes us to look at what are these things and what is happening there. These are about 17,000 light years away. The light traveled from there, took 17,000 years to reach us. That is the kind of image what you are seeing. Similarly, Spitzer Space Telescope is an IR telescope, infrared. In infrared, a nebula. So it looks like, Helix Nebula. It looks like eye. So these are the kind of images what you get. And from these images, you can look at some region of this image and look at the spectrum and see what is there, what is the kind of gas. So you understand more of how the stars are formed, how the planets are formed, how the stars die, and what happens after its death. All these aspects you understand from these images and the spectroscopy and polarization studies. And this another such, ghost nebula. It looks like a ghost. It is from the same satellite. And JWST, James Webb Telescope, I call upon the students to look at this. What is James Webb Telescope? Why it is so special? I am sure if it is working great, and if it continues work for next 10 years, I think it will touch many aspects of the universe, and probably including some aspects of life and life in other planets also. Go and have a look at it, and you see the bottom, that one picture. It is that telescope has almost as big as a tennis court size shield, sun shield, because it has to operate at very low temperature. It has that kind of shield, which is there. So again, all these challenges are, and a lot of money has been pumped in, new technologies have been developed, and all these great missions have been developed. So this is a great image from one of the great images of James Webb Telescope. This image has many star formation regions. Many regions there are new stars are being created, being born. So this triggers a lot of further studies. Now, we looked at some great missions outside. It's not limited to these 4 or 5 missions. We have a lot of other missions, and the technology, many have many different other technologies also. Now, coming to our own missions, and as you know, ISRO started with the aim to help the society. So what is required to help the society? We had a lot of problems like lot of poverty, hunger, etc. So that can be managed by better resource management. Resource is nothing but the resource on earth. So that with that intention, ISRO was started, and by the great Professor Vikram Sarabhai, and further Satish Dhawan, Professor U.R. Rao, all these people have contributed to realize this vision. And in that, lot of remote sensing satellites. You all know remote sensing satellites? So you would have seen, the forest fire or, the image of the earth, etc. from the sky. So this was used for resource management and resource, for example, agriculture and forest management, town planning. All these things these satellites were used. Google Map, for example, not from ISRO's satellite, but we have similar satellite and our own images. So Google Map, for example, it's from the remote sensing satellites. So a lot of remote sensing satellites have been built and launched. And then the communication satellite. Today, all the TV channels, they all are linked to some or other satellites. Many of them are linked to ISRO's satellite. So with remote, to enable this communication revolution have happened, etc. So to enable that communication satellite. And all these, once all these things are, created, enough infrastructure created through space infrastructure created for remote sensing and communication, we started looking at the science missions. Already, outside world was doing a lot of good science missions. So our first mission, you all know Chandrayaan-1, because that's a game changer, because that's where we started looking at science missions more seriously. And now we are seeing the benefit of that. One is, apart from, the technological leap what we are gaining, it also helps motivate youngsters like you and us. We all got motivated by many of these and joined these organizations. And planetary missions. And the objective of planetary missions, we have, especially the moon and Mars, we have interest because moon is very similar to Earth. And it was believed that moon was part of the Earth. And due to some impact, moon Earth system separated and the moon became separate. And how do you know that? How do you prove that? We prove that by studying moon in more details and comparing many aspects of moon with the Earth. And similarly, Mars has, it is very similar to Earth in many aspects, like the pressure there, etc., but not exactly same. And also there is a lot of proof that Mars had water, but there is no water now. So all these things raise many questions, like where the water has gone. So if we understand where the water has gone, we know that we will have the question whether Earth's water also will be there, or whether due to our activity we will destroy this planet also, whether we become like Mars someday, where nothing is there now. Apart from that, evolution of solar system and all. These are the motivation for planetary missions. And the basic question of any planetary mission is why the Earth is such a nice place to live, and will it always be so nice, or will it, are we, due to our activity, we will destroy them? So this is the thing. So Chandrayaan-1 has the best example of international collaboration. Many instruments were there, and through many Indian instruments, many collaborative instruments. So this is the typical satellite, how the instruments are mounted all around the satellite. And this is how we reach the moon. We start with a small orbit, we go on increasing the orbit, finally reach the moon. So there are complexity involved. We have to find precise, our velocity of our satellite, location of our satellite. Then it has to decide when to fire so that, it will go to the next orbit. All this complexity, very first successful attempt, first mission itself, we are successful in reaching moon and do a lot of good study. So these are all some pictures taken by Chandrayaan, and there are a lot of interest, there are studies going on. These are all open to even probably when you are graduate, even many of you can get these data and study. All these data is available in the public. These are all some lava tube, buried lava tube. It has interest because people think whether this lava tube can be used as a human habitat in future. So these are all the interests we have. Similarly, this is another picture of Chandrayaan, a 3D picture. So entire moon is modeled like that. So now we know where is crater, where is what, etc., which is very important for lander mission. And this is the mission where conclusively told that there is water in some form, right? Chandrayaan 1 is the first mission which detected water in some form on the moon. This is an American instrument, but flown on Chandrayaan. Then came Chandrayaan 2, and we know, how many of you think Chandrayaan 2 is a total failure or total success, or it's a partial success? Yeah, it's a partial success because orbiter is still there. And if the lander unfortunately could not land, I'm sure many of you have witnessed that, the heart-wrenching the situation. And you see the top one is the lander, bottom one is the orbiter. And orbiter is still around. These are some of the data from Chandrayaan 2 orbiter. This is a SAR, radar imaging data. And any geophysicist can use this data and understand the geology of moon. And this is another very high resolution. Chandrayaan 2 orbiter had highest resolution camera ever. So you can see the resolution was sub-meter resolution. The smallest, smallest of boulders also, rocks also you can see. It becomes very important because this can identify regions which is safe for landing. You can see moon has full of pits and boulders. And you cannot simply land. That's how Chandrayaan 3 lander or any lander mission becomes big news. And I just put this slide because this is the instrument I had the fortune to lead in developing this instrument. This instrument is sitting on this satellite. In fact, I cannot show in the, okay. This particular instrument is that instrument. And this is the instrument, lot of challenges in this instrument. Maybe, this is nothing but an X-ray spectrometer. When sun emits X-rays, right? And it hits the moon surface. From moon, you get fluorescence energy. You all know, I am told that, I have not seen, I am told that jewelry shops have this instrument, X-ray fluorescence spectrometer, to know that whether it is really gold or whether something else is there. Fluorescence gives that information. So from this instrument, you can understand what is the moon's surface elements, magnesium, aluminum, sodium, silicon. So depending on the ratio, you can understand the mineralogy. What is the mineral it is made up of. So this is one instrument which is working great. It has covered entire moon. These are some of the maps generated. Will not get into details. The spectrum is there, map is there. So these are data available now. A lot of people are looking at the data. And recently, we had a competition among IIT students, and to look at the data and bring out map. So computer science students took this data, brought out beautiful maps and generated 3D maps, etc. So that is what is available. Then we have Chandrayaan 3, and it had lander rover, and the most important thing is the landing site. Here, this is the place. You can see this is close to South Pole. In fact, it's called polar region because above 70, it is called polar region. It's close to 69.497 polar region. And all other earlier lander missions are in the equatorial region, where the region is well known. From ground itself, you can see. Polar region landing is difficult because sun comes at some angle, not much sunlight, and not known. So we landed in a very successful landing on Chandrayaan 3. And this is the landing location. Initially, it was surveyed, and that 2.4 kilometer by 4 kilometer landing site was identified, and that was targeted. and the precision required for landing. Probably, I think you can imagine. Once lander is close to move, you don't have much control. It has to take its own decision. Yes, as it is nearing the landing site, it has to slow down. Once it slows down, it has to descend. Slowly, as it descends, it has to reorient and if you travel by flight, the pilot will announce, now we are preparing for landing, we are ready for landing, etc. Because he changes certain things there, control systems, etc. But the lander has to do it automatically. And it has to get all the signals, sensors. All these sensors have to see, okay, you are seeing a, crater here, move. So you have to hover around and find, okay, this is a safe place. Finally, you go down in a particular velocity and land softly. That's what has been done. And this is the iconic picture of the Vikram lander. It is there, landed safely and proudly. And this is a rover, as you see, the Vikram and Pragyan. From Vikram, lander rover comes out and goes through all these points, and Pragyan, presently it is rested there peacefully, sitting there again proudly. And all these locations, it has done many measurements. And in fact, the papers published in Nature on these measurements, so you can look up. So these are the impactful missions. And then we had Mangalyaan mission and similar challenges. Sorry, I think the slide is missing here, no problem. Okay, Mangalyaan had another challenge, the communication delay, because it is much farther than Moon. And as it goes, it has to reorient, deboost, and get captured by Mars. So if you are not in the right time, right location, you will simply fly off. So getting captured by and getting into the exact orbit, you can imagine the kind of control system, kind of communication system, the sensors, and all the actuators which are required here, the technological challenges involved in this. So that's another proud mission ISRO had. Then AstroSat, I saw that no one heard about AstroSat. This is something I want once again the space works and those who are interested in space science to look into this. It was launched in 2015. This year we are celebrating 10th year, of course 10 year over. So 10th year we are celebrating AstroSat in a big way. It has produced many hundred papers. Of course, just papers won't be sufficient, but impactful papers. There are many impactful papers which has given this satellite has given. Again, a lot of challenges put in scientific missions require different orbit. Communication satellites will always be 36,000 kilometer height. Low Earth orbit, we know, but all these scientific missions, different orbit, because certain orbit you have a lot of particles, we don't want that. Certain orbit you cannot see the sources of interest. You have to change that. All these things are there. So it's put in 650 kilometers and 6-degree inclination from equator region. Many instruments, and the one of the instrument UVIT, ultraviolet imaging telescope, is best ever resolution telescope ever flown by anybody. And you can see the image here, the ground-based best image, and then you have ground-based optical image. In fact, this is the above GALEX, that is NASA's image, and the UVIT source image. You can see these are UV sources, ultraviolet sources emitting in ultraviolet. They give very detailed view. And XPOSat, again, I had the fortune of contributing one instrument here. This particular on the side, you have one instrument, and this side another instrument. These two have, look at the 2-degree field of view in the sky and study the objects like black holes, neutron stars, etc. And this is one such spectrum from this instrument. And this has already seen about 14 sources, 14 different sources in this 1 year. We target, okay, this source is of interest. We want to look at study it for a long time. and understanding. So we are doing that. I think this year we will see many very good findings from this mission, because people are working on analyzing the data, etc. And I just have another 3-4 slides, maximum 5 minutes I will finish. And then the solar science, you know Aditya mission, sun, sun is our star, which impacts our daily life. The known impacts like the seasons and all those things. Apart from that, there are many things which we do not know directly, we do not experience. Sun has what is called 11-year solar cycle. Every 11 years, the activity on sun peaks. Activity means sun becomes very active and starts giving out energy in X-rays and in energetic particles. It is called solar flare or CME, coronal mass ejections, very intense energetic particles. So it emits all these. How it impacts? It impacts because all those energetic particles hit Earth. Oh, this is called geomagnetic storm. So now we are dependent on a lot of space-based assets. Like we have our navigation. Today I could come to university without asking anything by putting Google Map. So this is based on using GPS satellites. So all these satellites have become basic infrastructure. So they have to survive. So these geomagnetic storms can destroy this satellite. There are many examples of destruction, and also power lines, transmission lines. I think some time back in Canada, the entire transmission line, because it has magnetic field, embedded magnetic field in that particle. So it can influence high current in the transmission line, so destroy the transmission line. So it is called space weather aspects. All the understanding space weather is very important. So studying sun, solar, apart from our own curiosity, why sun flares, what makes this sunspot and magnetic field and these emissions, all these things are important apart from your own understanding of science. In addition to that, how its impact on space weather, that is very important. So that's why a lot of solar missions are there. So, for example, this is an image, August 31st, 2012. Of course, there are many new images. You can see a flare. The flare is as big as size of the Earth. This is a flare in X-rays. You can see the bright region where sunspot flaring here. Sunspots finally, give out energy in the form of flares. So these flares impact aurora. So this aurora is created during these flares. If there is CME, these particles come and interact with the atmosphere and cause this beautiful aurora. So this is only what we see is only the beautiful thing, but it's other impacts are also. We understand that the space weather, geomagnetic storm impact on various aspects, various our infrastructure. So we have Aditya. The challenge in Aditya was to block the sun and study the corona. Corona means just outside the sun, because it's that region which tells the story of this flare and CME. So we want to understand that. So Aditya is such an instrument. The challenge here is to block the sun exactly and then study that. Even a little jitter will give you bright part of the sun, which can damage your instrument, or you will not be able to study. It is like, I cannot see the person sitting behind this light because this light is obstructing me. If I put this, I can see you much better. So that's what is nothing but coronagraphy. So when somebody flashes light, immediately you look at like this and see who it is, right? So this is the technique. This is a basic simple thing used. When you get eclipse, that time you get, but it's for very short duration. But you want to do that always. How you do? You put an artificial disk to block the sun and study the sun. And why Aditya is special? You can see SOHO, that is a observatory by NASA. You can see the sun is blocked up to here, this disk, from here to here. But actual sun size is this yellow circle. Now, that blocking, you're missing a lot of part. But Aditya can cover that because that violet circle is what Aditya outside that, and bigger, smaller circle to bigger circle, that region Aditya can cover. So that's why it is very, very significant mission and a lot of data coming. Today only I saw in breaking news that it has captured some very amazing one of the flare in April 2024, but scientists took time to understand that, analyze that. And the flare in the maximum detail they could see the flare and study. And this is how the spacecraft looks. There are many instruments here. You will not see what are these instruments, etc. And it is put in L1 orbit. You would have heard L1 orbit. Usually, Earth orbit only we put most of the things. L1 orbit means Sun, Earth. There is some point L1 at the not center, somewhat closer to Earth only. But that point is more stable, and it can look at Sun all the time, look at Earth all the time. So all the data, enormous amount of data, we can immediately transfer to Earth. If you're not in the line of sight, you will not be able to transfer the data. You have to wait until your antenna comes to the visibility of spacecraft. So L1 orbit, it is in this mission challenge. Now successfully it is completed in year. And then upcoming missions, we have Chandrayaan 4 sanctioned, Chandrayaan 5 almost sanctioned, and 6, 7, 8, 9, 10, up to 2047, many Chandrayaans are there. And finally, our Prime Minister himself announced that Indian will be on the moon by 2040. So that is the target we have. Obviously, we have to go. The human beings have to go, means lot of pre-missions have happened. Chandrayaan 4 will go and take some samples and come back and deliver. In our own center, our laboratory, we are building now to analyze that sample, because you may get only 2 kg sample. Just 2 kg soil from moon will come and we will analyze. So, again, I don't have to explain why you have to spend money and all, because we already discussed that. And the challenge here is why many countries are now running to, do lunar missions, because moon is considered as an outpost for human beings to go further to Mars or beyond. And when we go, we should have certain things like, we need water and sunlight, etc. So we are looking at a region where there is water nearby, or we can generate water, and you have sunlight. The polar regions are the best. In polar region, you find permanently shadowed region near the craters. You can see some of these pictures. You can see some of the craters. You can see dark. So those regions are considered, and it is understood that they have water in liquid form. And if you somewhere land goes, go and land close by, you have water resource, and also polar region have the eternal light. In our polar region, also if you go to Norway, Sweden, etc., you have almost even night. There is no night as such. Twilight always. So you will have such regions where you have some sunlight. And all these are challenges to manage this. You have to develop new technology and a lot of exciting technology, because you have to generate water from the soil. We have to get small sunlight but generate a lot of power. So efficient materials and technologies, chemistry, physics, all biological aspects, all aspects are involved in this. And if you see the below 3 pictures, same region has different times shadow. So it's very important to understand when you have shadow, when you have light, when you have when it is safe to land. All these aspects have to be studied and go there and land. And there are other missions which are under consideration. Venus orbiter mission, we are going to Venus. This is also a sanctioned payload targeted to be launched in 2028. And we are targeting that. A lot of instruments are there. Then there are many other missions like Transient Sky Monitor, study of exoplanets, planets which are outside our solar system, and high resolution UV imager, Mars lander mission, probably this year, hopefully we may get. probably sanctioned that also. Broadband X-ray polarimeter. These are all these missions are for you students to get, involved in. And just before last slide, astronomy, we talked about the curiosity, etc., but it impacts our daily life also because the technology developed is used in our day-to-day life also, many aspects of technology. I give 2-3 examples. Now that camera has CMOS imaging sensors. Before these CMOS sensor, CCDs were used. Probably CCD also, I'm not sure what the camera it is. And these CCDs are developed as a memory device. And it is astronomers who thought it can be used to store the astronomical data. So they pumped in money and invested and developed technology. And suddenly people realized, oh, it can be used in our camera. So now, all those things have come. And then image processing techniques. You get a lot of data, how you process. So your basic driving motivation is to understand that. So you do all that what is required. But the result is you find algorithms which are very efficient image processing algorithms which are used in our CT scan images, for example. Effort required, technology required, kind of reward it gives. And where India stands as on today, the plans we have, so the astronomy benefits from the technology and drives the technology is the keyword. And with this, I conclude my talk. Thank you for your attention. And once again, Carl Sagan, a great communicator, his statement somewhere, something incredible is waiting to be known. It is happening, but waiting to be known. It is up to us to explore it. Go and read and lot of lectures, videos about Carl Sagan. And it's very great, inspiring. Thank you very much. Yeah.
ಜನಸಾಮಾನ್ಯರು ನಾವು ಮಾತಾಡ್ಬೇಕಾದ್ರೆ ಯಾವ್ದೊಂದು ಕ್ಲಿಷ್ಟತಮ ವಿಷಯ ಇದ್ರೆ ಒಂದು ಬೆಂಚ್ ಮಾರ್ಕ್ ಇಟ್ಟಿದ್ದೀವಿ ರಾಕೆಟ್ ಸೈನ್ಸ್ ಅಂತ. ಇದು ಅಂತ ರಾಕೆಟ್ ಸೈನ್ಸ್ ಎಲ್ಲ ಮಾಡ್ಬೋದಪ್ಪ ಅಂದ್ರೆ ಅಂತೇನ್ ಕಷ್ಟ ಅಲ್ಲ ಅಂತ. ಇವತ್ತು ನಿಜವಾಗ್ಲೂ ರಾಕೆಟ್ ಸೈನ್ಸ್ ಅತ್ಯಂತ ಸರಳವಾಗಿ ಸುಲಲಿತವಾಗಿ ಎಲ್ರಿಗೂ ಅರ್ಥ ಆಗೋ ರೀತಿಯಲ್ಲಿ ಹೇಳಿದ್ದೀನಿ ಸರ್. ಡಾಕ್ಟರ್ ರಾಧಾಕೃಷ್ಣನ್ ಅವರಿಗೆ ಈಗ ವಿಶ್ವವಿದ್ಯಾಲಯದ ಪರವಾಗಿ ಗೌರವ ಸಮರ್ಪಣೆ ಮಾಡ್ಬೇಕಾಗಿ ಸನ್ಮಾನ್ಯ ಕುಲಪತಿಗಳನ್ನ ವಿನಂತಿ. ಒಂದು ಕಡೆ ಒಂದು ಮುಖ್ಯವಾದ ಪ್ರಕಟಣೆ ಇದೆ. ರಾಷ್ಟ್ರೀಯ ವಿಜ್ಞಾನ ದಿನಾಚರಣೆ ಅಂಗವಾಗಿ ಕಾಸ್ಮಾಸ್ ಮತ್ತು ಮೈಸೂರು ವಿಶ್ವವಿದ್ಯಾಲಯದ ಸಹಯೋಗದಲ್ಲಿ ಇಂದು ವಿಜ್ಞಾನ ಭವನದಲ್ಲಿ 6:30 ನಂತರ ಸ್ಕೈ ವಾಚ್ ಪ್ರೋಗ್ರಾಮ್ ಇದೆ. ಟೆಲಿಸ್ಕೋಪ್ ಮೂಲಕ ನಾವೆಲ್ಲರೂ ಕೂಡ ಬಾಹ್ಯಾಕಾಶವನ್ನ ವೀಕ್ಷಿಸಬಹುದು. ಆಸಕ್ತರು ಇದನ್ನ ಸದುಪಯೋಗಪಡಿಸಿಕೊಳ್ಳಿ ಅಂತ ಹೇಳ್ತೀನಿ. ಹಾಗೂ ಇಂದಿನ ಈ ಸಮಾರಂಭದ ಅಂತಿಮ ಘಟ್ಟವನ್ನು ನಾವೀಗ ತಲುಪಿದ್ದೀವಿ. ಈ ಸಮಾರಂಭದ ಯಶಸ್ಸಿಗೆ ಕಾರಣೀಭೂತರಾದ ಸರ್ವರಿಗೂ ವಂದನೆಗಳನ್ನ ಸಲ್ಲಿಸಬೇಕಾಗಿ ವಾಣಿಜ್ಯ ಶಾಸ್ತ್ರದ ಹಿರಿಯ ಪ್ರಾಧ್ಯಾಪಕರು ಹಾಗೂ ಪರೀಕ್ಷಾ ಕುಲ ಸಚಿವರಾದ ಪ್ರೊಫೆಸರ್ ನಾಗರಾಜ್ ಅವರನ್ನ ಅಭಿನಂದಿಸ್ತೇನೆ.
ಎಲ್ಲರೂ ಅಪ್ಪಾದ್ರೆ ಅವ್ರ ಸಮಸ್ಯೆ ಒಂದೊಂದು ಬರ್ತಾರೆ ಅದೇ ಅದಕ್ಕೆ
Respected chief guests, esteemed dignitaries, the honored guests, fellow members, and all the attendees. A very good morning to all of you. It is both a privilege and an honor to stand before you today on behalf of the University of Mysore to express my sincere gratitude for making this National Science Day ceremony an unforgettable occasion. First and foremost, we would like to extend our heartfelt thanks to Dr. Radhakrishna, the scientist of the Space Astronomy Group, ISRO Bangalore. Your dedication, hard work, and groundbreaking contribution to the field of space science are truly commendable, sir. Your presence is an inspiring aspect to all of us, and your achievements continue to motivate our student community in general and future generations in particular. We are proud to have you with us, sir, for drawing us to your cosmic energy. A special word of appreciation goes to our Professor Lokanath, sir, the Vice Chancellor of the University of Mysore. On behalf of the university, we also personally thank on behalf of the student community, sir, for this great auspicious occasion. Your unwavering commitment to academic excellence has profoundly shaped the future memories of the students, for the numerous students, and your leadership continues to guide and inspire us, sir. So we thank you, sir, personally and also on behalf of the gathering here, and your constant encouragement and support for making this day a successful one. We extend our heartfelt thanks to the syndicate member, academic council members, deans of the faculty members, and the media personnel, and all our university teaching and non-teaching faculty members. Your presence and valuable contributions have made us this day a memorable event in the annals of the University of Mysore, and we are deeply honored for your participation. Finally, I would like to express my sincere gratitude to each and everyone for being a part of this important occasion. Let us continue to celebrate the spirit of science, discovery, and the intellectual growth, and work towards creating the brighter and most prosperous future together. Thank you once again. May we continue to strive for excellence in all our future endeavor. Thank you very much once again.
ಈಗ ಕಾರ್ಯಕ್ರಮವನ್ನ ರಾಷ್ಟ್ರಗೀತೆಯೊಂದಿಗೆ ಸಮಾಪ್ತಿಗೊಳಿಸ್ತಾ ಇದ್ದೀವಿ.
गणमनाधिनायक जय हे भारत भाग्य विधाता पंजाब सिंधु गुजरात मराठा द्राविड उत्कल वंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जनगण मंगल नायक जय हे भारत भाग्य विधाता जय 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 जय
ಕಾರ್ಯಕ್ರಮ ಮುಕ್ತಾಯಗೊಂಡಿದೆ. ವಂದನೆಗಳು.